Hi there, my name is Abhishek Chugh, and in this video I describe how knowledge from Metamath databases is organized in Sophize. Let's begin by looking at the proof page of double mode exponents, one of the simplest theorems proven in Metamath. Let's see how different parts of the page map to Sophize concepts. Unsurprisingly, the assertion, along with its set of hypotheses, is called a proposition in Sophize. In Sophize, the presentation of this proposition is slightly different, but the exact same information is maintained. However, the proof of the proposition is handled a bit differently. We call such a proof an argument. In this case, the argument has one premise, which is the axiom of mode exponents, and the conclusion is, of course, the double mode exponents proposition. This argument consists of the same 5 steps as we saw before, but the argument also maintains the list of premises and a conclusion. This information can also be graphically represented like so. Now let's look at NP2old, which is an alternate proof of the same proposition. The difference here is that the argument uses one additional premise, MPI, to reach its conclusion. In Sophize, this proof results in a new argument that reuses the same conclusion as we saw before. This is represented visually like so. Continuing the same way, we build the argument graph using all the proofs available in the set.mm database. On its own, the argument graph doesn't have sufficient information to claim if any proposition has been proven or not. To do that, we need to combine our argument graph with a belief set. A belief set is nothing but a set of axioms that we assume to be true without the need for any supporting arguments. Combined with the belief set, the argument graph turns into a directed acyclic graph that contains a proof for every statement that it claims to be true. Let's see what this looks like. In set.mm database, mode exponents, AX1 and AX2 are axioms. Starting with these propositions, we look for arguments that prove other propositions in the argument graph. In the first phase, we find 3 arguments that only require these axioms as premises. Next, we find that MBT can be proven from our current list of proven propositions. And then, finally, we prove MPI, whose argument uses MPD and A1I as premises. Note that the argument NP2old was not used in this proof graph. Let's look at another belief set where AX2 is not included. In this belief set, only 4 propositions will be considered to be true. There are no proofs for the rest. I would like to note that a belief set can contain any propositions, not just the ones that we traditionally consider to be axioms. For example, let's consider the belief set where A1I is an axiom and AX1 is not. That would result in a proof graph that looks like this, and the system generates proofs based on your belief set. Now let's switch to Sophize to see all this in action. This page shows the belief set that contains all $A turnstile type propositions in set.mm database. There are 909 propositions that make up the axioms and definitions in set.mm. Now let's take a look at the proof of mode exponents reduction MPD in this belief set. We click on the root node of the proposition to show the final argument in favor of MPD. This argument requires 2 premises: the axiom of mode exponents, which is axiomatically true in our belief set, and A2I, which is true because of another argument that needs the axioms AX2 and mode exponents again. These 2, of course, are also axioms in our belief set. So this tree shows the complete proof of proposition MPD in set.mm database. Let's look at a more casual example of belief sets. This belief set is a close representation of my understanding of numbers and how to add them. It consists of 40 things I learned about numbers in school. Preschool nursery rhymes taught me that the number 5 comes after the number 4. In middle school, I learned about the commutativity and associativity of addition. By then, I also knew about how addition works with carryover. And by the end of high school, I knew that 0 and 1 are complex numbers. Like most of my friends, I found these to be obvious, or I was just fine memorizing these as facts. I didn't feel the need to know why they were true while I was learning them. So let me go ahead and select this belief set and see a machine-generated formal proof for addition of numbers that I can understand. Now we are on the page of a machine that generates formal proofs for addition of natural numbers. If you don't know about machines yet, do check out our video on proof generating machines. For now, you just need to know that like propositions can be proven or unsolved in a belief set, proof generation machines can be activated or deactivated based on the axioms in the belief set. The custom belief set that we just talked about does activate this machine. Okay, so let's add two numbers, 18 and 7. The machine says 18 and 7 add up to 25. Let's explore the proof returned. The final argument makes sense to me. 8 plus 7 is 15. The 1 carries over to make 2. And the final result is 25. Now let's look at the premises. EQID, which is A equal to A, is obviously true for me. It is there in my belief set. 1 is n and 0, that is 1 is a whole number. This is true for my understanding because A, 1 is a natural number, I know this, and B, all natural numbers are whole numbers. My 4th grade teacher taught me that. So this is a fully formal proof tailored to my understanding, not a maze of some mysterious objects starting from symbols without meaning that I can't really hope to navigate in this lifetime. So what you saw was obviously a highly contrived example to let you understand belief sets. However, belief sets, and more generally, Sophize data organization scheme can have significant applications for Metamath users. Perhaps the most obvious use case is that they allow you to avoid duplicating the same propositions and arguments across different theories. By reusing arguments applicable across multiple belief sets, we avoided duplicating thousands of proofs that are identical in set.mm and iset.mm databases. The organization model will become much more useful as the Metamath community starts work on more and more theories. Want to see which theorems are true in Euclidean, hyperbolic, and elliptic geometries? All arguments from absolute geometry will automatically be shared across all three theories. Each geometry needs only to add the arguments utilizing their version of the parallel postulate. Another use case would be to understand the consequences of important conjectures like the Riemann hypothesis. Want to know what happens when the continuum hypothesis is true or when it's false? Just create two belief sets and develop proofs from each point of view for the world to see. And why just restrict to pure mathematics? You can create a proof on the breakdown of internet security system if the traveling salesman problem can be solved in O n cube time. The proof doesn't need to be fully formal from day one. Sophize allows combining informal arguments with formal proofs. The Metamath community also seems to have an interest in formalizing historical works. Sophize can help you share with the world how the foundation of mathematics were developed over time by Cantor, Russell, Whitehead, and Frege. Our video on articles in Sophize might be of interest to you. Please share your thoughts, questions, and suggestions in the comment section below. Thanks for watching.